That was a test question. Maybe. I don't know. It could have been. Should have been. So my point to you here is we got 0, we got 0, we got 0, and over here we got 1. This, on the other hand, 0, 1, 1, 0. But we can define an addition and a multiplication on these equivalence classes. All right? You might recognize this if you've had like a course in discrete math. I don't know if you guys have it or not. Some of you maybe. This is essentially the statement. What is this? Like, notice that 0 is also this, right? The 2 is also in this an even number, right? In fact, there's infinitely many representatives for that equivalence class. 0 is just a nice one. But you could put 2 here, you could put 4 here, whatever. And you see how this goes? We have 1 plus 1 equals to what? It's equal to 2, right? But 2 is also equal to 0 here in terms of the equivalence class. This is the binary number system. This is addition and multiplication, quote unquote, mod 2. All right. Anyway, we'll talk more about this systematically in a future lecture, but I'm just kind of showing it to you at the moment as a nice example of the concept of equivalence class, all right, in terms of even and odd. Now, one of the major theorems that we have about equivalence classes is that they do what's called, they form what's known as a partition of the set on which we're forming an equivalence relation. What's a partition? That's what I need to define next. So like, let me just point out here before I guess I'm going to erase that, but notice that the integers are, it's the even integers unioned with the even, well, I forget my notation. See, you can go either way. You can put the plus 1 before or after the 2z, really, but I'm trying to be consistent. We'll talk more about this when I have a little more time, but so the even, right? In other words, even unioned with the odds, right? Even union odds gives me the whole integers. And is there any commonality? Like, what's the deal? What's the intersection of even and odds?
The empty set.
The empty set, right. So this means that the equivalence relations of this equivalence relation we're just looking at, the equivalence classes of this equivalence relation we're looking at, they partition the integers. We have a partition of the integers into even and odd numbers. That is, we have a pair of disjoint sets whose union forms the whole thing. Now, it doesn't just have to be a pair. The concept of a partition is more general than that. Partition could have infinitely many sets in it. But the deal is that a partition of a set, it has to be a collection of subsets, a collection of non-empty subsets, I should say, whose union forms the whole set, and whose pairwise intersection is empty. So definition. This is a partition that we're defining. And there's an unfortunate typo in this definition I need to correct. All right, so let S be non-empty. All right, non-empty set. A family of subsets, let's call it A, is called a partition called a partition if number 1, each subset in A is non-empty. All right. 2, for all, let's say, u and v in A, all right, either u is equal to v or u intersect v is empty. In other words, it's a family of distinct subsets which are pairwise disjoint. There's no intersection between any two subsets forming this family. And then 3, the union over u and A, all right, of u is equal to S. So the union of all the sets forming the partition gives us the entire set. This is a partition. All right, so an example, let's see here, example, what am I on? 5. We could let A equal to, let's say, like n to n plus 1, such that n is an integer. This gives partition of the reals. I can draw a picture of it, right? Like, here's my number line, right? And you got like, 0, right, to 1. That's one of them, right? Next up, 1 to 2. Right, that, and so forth and so on, right? It's pretty clear. We can prove that if you take two subsets in the partition, they're what? They're either disjoint. Well, first of all, if we take distinct subsets of the partition, it's fairly obvious that they're disjoint, right? So, do you agree? So this is a partition of R, because it's also clear that if you take the union, right, over n in the integers of this, we get everything, right? I don't want to prove it today, but I think it's fairly evident that that's true, right? Example 6, if I tried to use almost the same thing, but close bracket, right? This wouldn't work. Why? Notice that like 0 to 1 intersect with 1 to 2 has 1 in it, right? So these are not disjoint. Therefore, A, not a partition. And of course, this is just a particular counterexample. In the notes, I point out that if we take the intersection of two subsequent ones, we always get n in it, right? So it is true, though, that it satisfies like axiom 1 and axiom 3, right? They're non-empty subsets of the reals, and their union does cover everything, but they're not disjoint, right? So they're not a partition. Partitions have to be disjoint. Any questions? Can you guys think of another way to partition the integers that we haven't done today? Like, how about this? Example 7. What if we did, like the integers, we could do like 3z unioned with 3z plus 1 unioned with 3z plus 2, right? Would that give a partition? So 3z, what I mean by that is things of the form 3m such that m is an integer, right? And 3z plus 1, what's that mean? We're talking about like 3j plus 1 such that j is an integer, right? And 3z plus 2, we're talking about a set of the form 3k plus 2 such that k is an integer. Do these form a partition?
Yes.
Yes, I think you're right. Now, proving that, given our current technology, is a little tough. All right? We basically proved this for even odd. But I had to go to some effort to prove it. I had to use the division. I used division to get this to be true, if you go back and look at my argument. So we could start with, like, small things. Like, suppose that you have, let's just, for the sake of specificity here, we could show that they're disjoint, right? If I had x is an element of 3z and, say, 3z plus 1, what would that mean? That would mean x is equal to 3j plus 1, and it's also equal to 3m, right? For some m and j and z. But what would that tell me? That would tell me that that would tell me that 1 is equal to 3 times m minus j, right? Which would imply that 3 is equal to 1 over m minus j, right? Well, okay, if m is equal to j, it's 0. We get 0 equals to 1, which is a contradiction, right? If m is not equal to j, we can divide by m minus j. And then I get that 3 is equal to 1 over m minus j, which is clearly absurd, right? Because 3 is not equal to a fraction that's less than 1. I could put some teeth on this if we studied, like, various inequalities and things, but it should be fairly evident that if x is an element of both of these sets, we get a contradiction. Consequently, there is no x that's an element of both of the sets. So you're right. It does form a partition, it looks like. Now, we have not yet proved that any integer can be written as a sum of 3 such things. I mean, excuse me, we have not yet proved that any integer falls into one of these 3 classes, right? I say classes. What do I mean, classes? I'm suggesting that this is an equivalence. I'm suggesting that these are, in fact, equivalence classes, that this is, in fact, the set of equivalence classes for an equivalence relation. Guys, care to tell me what equivalence relation produces these as their equivalence classes? Like, what would you say? What do you think? X and y and z, then x equivalent to y, if and only if what? X minus y is an element of what? This is a creative leap. You're not supposed to understand this on the basis of what we've done today or anything like that. All right, I'm kind of jumping ahead a bit, but if you think about it, it's going to be 3z here. Right? So that's the equivalence relation that's hiding behind this particular partition of the integers. The difference is a multiple of 3. All right? So what we're going to prove at the start of next class is that this is not an accident. To every partition of a set, there corresponds an equivalence relation. And to every equivalence relation, there corresponds a partition, the partition being simply offered by the equivalence classes of said partition. This is one of the fundamental theorems that allows us this transference between partitions and equivalence relations, which is super important. And so we'll dive into that at the start of next class. But anyway, thanks, guys. Again, my apologies about problem, what was it, 37 or 47B? So